Alright, so we're going to introduce two more theorems. One with derivatives of Laplace transforms, and the other one with integrals with Laplace transforms. So the hypothesis is the same. So suppose the Laplace transform of little f is big F. Then the inverse Laplace transform of big F prime is negative t times little f. And the theorem for integrals states something similar. If the Laplace transform of little f is big F, then the inverse Laplace transform for the integral of big F is little f divided by t. Alright, so we're going to use these two theorems to do some examples. So let's do that. Okay, suppose we want to find the Laplace transform of t cosine 2t. So same thing, let's do the chart. We have a column of little f and a column for big F. They are linked via Laplace transforms and inverse Laplace transforms. We want to find the Laplace transform of t cosine 2t, but we don't want to take the integral. But we realize that t cosine 2t is negative cosine 2t multiplied by negative t. And we know the Laplace transform of cosine 2t from the table. So this is equal to negative s over s squared plus 4. So according to the theorem, the Laplace transform we're looking for of t cosine 2t is the derivative of negative s over s squared plus 4. Alright, so it remains to find the derivative of this function. Quotient rule. Minus negative s times 2s. This thing is squared, so it's s squared plus 4 squared. And it's s squared minus 4. So this is the answer we're looking for. We didn't do any integrals at all, so it's convenient. Right, so let's do a different example. Now suppose we want to find the Laplace transform of hyperbolic sine over t. So same thing, let's create two columns via Laplace and inverse Laplace transform. So we want to find the Laplace transform of sinh t over t, but we don't want to integrate anything, so we resort to look for the table to find the Laplace transform of sinh t first. So if we look at the table, the Laplace transform of hyperbolic sine is equal to 1 over s squared minus 1. And according to the theorem, because here we're dividing by t, so the Laplace transform we're looking for is the integral of this function. So the official answer will be the integral from s to infinity of 1 over sigma squared minus 1 d sigma. Alright, so let's actually evaluate this integral. So 1 over sigma squared minus 1 factors as sigma plus 1, sigma minus 1 d sigma. And if you use partial fractions, this is 1/2 1 over sigma minus 1 minus 1/2 1 over sigma plus 1 d sigma. And this is equal to 1/2 natural log of sigma minus 1 minus 1/2 natural log of sigma plus 1 from s to infinity. And combine the two things, 1/2 ln of sigma minus 1 over sigma plus 1 from s to infinity. At infinity, this fraction goes to 1, ln of 1 is 0. So that part that doesn't count. So the only part that counts is the s part, which is negative 1/2 ln s minus 1 over s plus 1. Moving the negative sign, so it's 1/2 ln of s plus 1 over s minus 1. So this is our answer. All right, so we can also use the theorems to find the inverse Laplace transforms. So suppose we want to find the inverse Laplace transform of natural log of s plus 3 over s minus 1. First, we realize that natural log of s plus 3 over s minus 1 is natural log of s plus 3 minus natural log of s minus 1. So remains to find the Laplace transforms of the two individual terms. So let's draw the table again. So we want to find the inverse Laplace transform of s plus 3 and ln of s minus 1. But we don't know how to find the inverse Laplace transform of them. But we know when we take the derivative, the natural log goes away. So all we have is 1 over s plus 3 and 1 over s minus 1, which we know how to find the inverse Laplace transform. So according to the table, the inverse Laplace transform of these two functions is e to the negative 3t and e to the t. And the theorem tells us that if it comes from the derivative, then all we need to do is divide by negative t here. All right, so here we have two things we need. It's e to the negative 3t divided by negative t and e to the t divided by negative t. So these are the correct inverse Laplace transforms of the natural logs. So the inverse Laplace transform of the difference is the difference of these two terms. So the first one minus the second one is equal to e to the t over t minus e to the negative 3t over t. Right. One more example. Suppose we want to find the inverse Laplace transform of 2s over s squared minus 1 whole thing squared. So we could use partial fractions, but let's try to use the theorem we just introduced to make things easier. So little f and big F link via L and L inverse. The function we need is 2s over s squared minus 1 squared. But we notice that this function is actually the derivative of negative 1 over s squared minus 1. These two functions are linked via derivatives. And we actually know how to find the inverse Laplace transform of this simpler function. If you look at the table, that's gonna be sinh hyperbolic sine with a negative sign here. All right, so according to the theorem, taking derivative in capital F is the equivalent as multiplying by negative t in little f. So all we need to do is multiply this hyperbolic sign with negative t. So we get t times, technically negative t times negative hyperbolic sine of t, which is equal to t hyperbolic sine of t. And that's our final answer. Yep. So no new integrals, which is very convenient.